Alright, so let's move on to an example where we actually have an ion instead of a neutral molecule. So the only difference here for the hydronium ion, H3O+, is that we have to account for the fact that the entire molecule, or since it's got a charge, polyatomic ion, has a charge, so it has a different number of electrons than if we just combine 3 hydrogens and a single oxygen atom together. So we can tell from our formula, H3O+, that this has a positive 1 charge. So it has 1 fewer electron than it would have if we just combined 3 hydrogens and oxygen and didn't add or remove any electrons. So the way we're going to count up the number of electrons is we have 1 from each of our 3 hydrogens. So 1 times 3 is 3. Oxygen has 6 valence electrons, so 3 and 6 is 9. And then we need to subtract 1 electron for our positive 1 charge. So 9 minus 1 is 8. So we have 8 valence electrons in this structure. Step 2 is to combine all of our atoms and figure out what the central atom is. So again, the central atom can't ever really be hydrogen, so it's going to have to be oxygen, just like it was with water. And for each of those 3 hydrogens to be part of the molecule, we're going to need to attach it to our central oxygen. So we have 3 hydrogen-oxygen single bonds, meaning that we used up 3 times 2, since each of those is a bonding pair. We used up 6 electrons, meaning we have 8 minus 6 is 2 electrons left after step 2. We can't do anything in step 3 because hydrogen should only have 2 electrons around it, so we shouldn't add any lone pairs to that. So step 4 says take those 2 remaining valence electrons and apply them to our central atom, oxygen. And so we do that, and you can see oxygen now has a lone pair of electrons around it. There's nothing to do in step 5 because we have 1 lone pair and 3 bonding pairs for 4 pairs, or 8 total electrons around oxygen. So there's no need to form any double or triple bonds. And we couldn't anyway, since our hydrogens don't have any lone pairs to donate to form double or triple bonds. And so step 4, we're basically done. The only thing you need to take into account is that if you have an ion, to draw the formula correctly, you put the whole thing in brackets and then you indicate the charge, basically as a superscript to the right, kind of like you would the same position in a chemical formula. So you use brackets and indicate the charge if it's an ion. So what you see there after step 4 with the brackets and the +1 charge in the upper right corner is the correct structure for the hydronium ion, H3O+. Okay, so in all the previous examples we've looked at so far, I've told you that there was nothing to do in step 5, so let's change that up a little bit. So for this example on the slides, it asks us to draw an electron-dot structure for CH2O. This molecule happens to be formaldehyde, if you've ever heard of that compound before. So, as always, step 1 is to count up how many valence electrons we have. Carbon has 4, hydrogen has 1, there's 2 hydrogens. Oxygen has 6 valence electrons. If you add all those together, you get 12. So we have 12 electrons to draw in this molecule. Now, step 2 is going to be to figure out how to connect our atoms together. Now, hydrogen's never going to be the central atom, so how do we decide between carbon and oxygen? There's a couple of ways. So again, remember, carbon's pretty much always going to be in the center of a molecule if it's part of the molecule at all. So based on that, we can probably assume that carbon should be at the center. Also, carbon is less electronegative than oxygen. That's another good indication that it is a better candidate for the center of the molecule than oxygen is. And finally, if you go back to the chart, which shows you the expected number of bonds for row 2 elements, carbon is usually going to have 4 bonds around it, whereas oxygen typically only has 2. So since carbon generally forms more bonds, that is also a good indication that it will be at the center of the molecule. So all lines of evidence point to the fact that we should have carbon in the middle, and then 2 hydrogens and our 1 oxygen as terminal atoms. So each of those terminal atoms, the 2 hydrogens, the 1 oxygen, need to be bonded to our central carbon atom, and for each of those we need one bonding pair of electrons. So that used up 6 electrons of the 12 we have to put down. So after step 2, step 3 tells us to assign electrons to the terminal atoms, except for hydrogen, to complete their octets. So we don't add any electrons to hydrogen, but we do have our oxygen, which after step 2 only has 2 electrons around it, which is much less than the 8 that it would like to have. So what we're going to do is we put 3 lone pairs around oxygen, for the reason that it needs 6 more electrons to get to a total of 8. So 3 is the correct number of lone pairs to do that. And as it turns out, we had exactly 6 electrons left after step 2. So in step 3, we've accounted for all of the electrons in the molecule. There's no more to put down. So in step 4, there's no electrons to add to the central carbon atom, so we're not going to do anything there. We don't have any electrons left to do that. Now, we get to step 5, and here's where things become a little bit more interesting compared to the previous examples. If you check on our carbon in step 5, it only has 3 bonding pairs around it, and no lone pairs. So 3 times 2, since each of those is a pair, that gives us 6 electrons around carbon, and we should have 8, remember. So how can we fix that? We don't have any more electrons to put down, so we can't give it a lone pair. What we can do is we can take one of those lone pairs from oxygen, and instead of having it belong to oxygen exclusively, we can share it between the oxygen and the carbon. If we do that, the oxygen will still have 8 electrons around it, because it has access to those via bonding, but now the carbon can access those 2 electrons as well. So we're going to take a lone pair and turn it into a bonding pair between carbon and oxygen. And since we already had a bonding pair there, that means we're now going to have 2 bonding pairs, and so a double bond, which we can indicate with a pair of parallel lines. Remember, the number of parallel lines that you see between 2 atoms in a molecule corresponds to how many bonds there are between them. So in step 5, we go from a situation where we have a carbon-oxygen single bond and 3 lone pairs around oxygen to now 2 lone pairs on your oxygen and a double bond between carbon and oxygen. And if we check that, carbon now has 4 bonding pairs of electrons around it, 1 with each of the hydrogens and 2 pairs with the oxygen. And 4 pairs times 2, since there's 2 electrons in a pair, gives us 8 electrons. And so carbon now has a complete octet. So that structure you see at the bottom right of this slide is the correct structure for formaldehyde. Alright. So that's an example with some multiple bonds. Let's look at an example like sulfur hexafluoride. This is an example where we'll see an atom where we go beyond the octet rule in terms of the number of electrons around one of our atoms. So sulfur, in particular, is in row 3, so that means that it is a large enough atom that there will be some situations where it will have more than 8 electrons around it, and sulfur hexafluoride is going to turn out to be one of those examples. So if we kind of go through this, in step 1, the first step is always going to be to count up the valence electrons. Fluorine's a halogen, so each fluorine has 7 valence electrons. There's 6 of them. The formula SF6 tells you that. So we have 6 times 7 is 42 electrons contributed from our fluorine atoms. And then sulfur, being in the same column as oxygen, has 6 valence electrons, so we need to add 6 more to that. So that gives us a pretty large number of valence electrons at 48. So we have 48 electrons to place down in this molecule. Step 2 says we need to pick the central atom and connect our other atoms to that. And fluorine only ever forms 1 bond, so fluorine's not going to be at the center of this molecule. Sulfur will. So we'll put sulfur in the middle of this molecule and attach all 6 of our fluorines to that. Remember, each of those fluorines needs to be bonded to the central atom for it to be part of the molecule at all. And once you've done that, we have 6 sulfur-fluorine single bonds for a total of 12 electrons used, meaning we have 36 electrons left after step 2. So we can use those to complete the octets of the fluorine atoms in step 3. We have 6 fluorine atoms, each of which needs 6 more electrons to get to a total of 8. And as it turns out, if we have 6 electrons per atom and 6 atoms, that'll be 36, which is exactly the number of electrons left after step 2. And so in step 3, we have sulfur in the middle, we have fluorines, 6 of them around the sulfur, and each of them has 3 lone pairs of electrons around it. And that accounts for all 48 electrons, so we don't have any more electrons to place after that. So nothing to do in step 4. Step 5 is to check the octet of your central atom, and if sulfur had fewer than 8 electrons around it, what we would need to do is to form some double, maybe some triple bonds. But if you look at your sulfur, it has 6 bonding pairs of electrons around it. Each of those sulfur-fluorine single bonds is a pair of electrons. So sulfur doesn't have 8 electrons around it, it actually has 12 electrons. Now sulfur being in row 3 is large enough that there will be some situations where it can do that, but we certainly don't need to add more electrons to it. It's already got more than you'd predict based on the octet rule. So after step 3, there's no more changes to be done, and that's your final structure. Okay, so let's look at this next example. This will be another so-called hypervalent molecule, and these are just ones that violate the octet rule by having more than 8 electrons around the central atom. And there's actually a typo in this slide. We'll cover that when we get to it. So this problem asks us to draw an electron-dot structure for ICl3, iodine trichloride. Both iodine and chlorine are halogens, so each of them will have 7 valence electrons per atom. So we have 1 iodine, so 7 from that, and then 3 chlorines. 3 times 7 is 21 for that. So 7 plus 21 is 28 valence electrons. Step 2 asks you to put the molecule together, at least the skeleton of it, essentially. And between iodine and chlorine, iodine is less electronegative than chlorine, so it's a better candidate to go in the central part of the molecule. So we'll take our iodine, we'll attach the 3 chlorines to it with 3 single bonds. Step 3 asks us to complete the octets of those outside atoms, the chlorines, and each of them only has a single bond after step 2, so we're going to use 6 electrons in the form of 3 lone pairs around our chlorine atoms, and that'll bring us to a total of 8 times 3 is 24, so we have 24 electrons used up after step 3. So that means we have 4 electrons left since we started with 28. So we don't have any more room around the outside chlorine atoms to place those electrons, so we're going to be forced to put them around our iodine atom. So if we have 4 electrons left, that means we can put 2 lone pairs around iodine. And you may notice that between step 3 and step 4, this chlorine on the left part of the molecule seems to have lost a few electrons, and that's not supposed to be the case. So all 3 lone pairs that we put on that previously should still be there. So there should be still those 3 pairs of electrons, which are double dots around that chlorine. So there should be 3 lone pairs there. And after step 4, we've correctly used up all of our valence electrons, so there's no more to place. Step 5 is to check on the central atom, which is iodine. Make sure it has at least 8 electrons around it. And iodine has 3 single bonds to chlorine, so that's 3 bonding pairs, and then we put 2 lone pairs on it as well. So that's a total of 5 pairs of electrons around iodine, so 10, which is actually more than 8. Iodine's pretty low in the periodic table, so that's not an inconceivable situation for that. But it definitely means that we don't need to form any more bonds to our central iodine atom. And so what we have after step 4, assuming that all 3 of our chlorines still have their lone pairs, is the correct structure for that molecule. Okay, so the next thing we're going to get into is radicals, and radicals, or free radicals, are a type of molecule where we have unpaired electrons in our Lewis dot structure. These are not very common because, of course, the octet rule says all of our atoms should have 8 electrons around them, or I guess 2 if they're hydrogen, but those are all even numbers. So how could we end up in a situation where we have unpaired electrons? Generally speaking, this is going to be when we have when we count up our valence electrons and we have an odd number of electrons. And the rule is basically the same. We're going to go through things and do them in the same way. We're just going to end up in a situation where we have an atom that doesn't have an octet around it, and generally speaking there will be one less electron than you would predict based on the octet rule. So for an example of this, we can look at nitrogen dioxide. This is one of the few relatively common free radicals that you might see in a Lewis dot structure. So nitrogen dioxide, NO2, not to be confused with a nitrite ion, NO2 minus. So this is just a neutral NO2 molecule. If we count up the valence electrons, nitrogen has 5 of them, the oxygen has 6, and there's 2 oxygens, so that gives us 17 electrons. So that's an odd number. If that seems strange, it's because all of the examples we've seen so far had an even number of electrons. So with the 17 electrons around, well, available for our molecule in general, what you would do is you would put your nitrogen in the middle. Nitrogen forms 3 bonds generally, oxygen only 2, and nitrogen's less electronegative than oxygen as well, so it's a better candidate for the central atom. So you put the nitrogen in the middle, we attach the 2 oxygens to it, we complete the octets of the oxygen atoms, and we end up with exactly 1 electron remaining to put on our nitrogen in step 4. So we just put a single dot down instead of a pair of electrons, because after putting down that 1 extra dot on nitrogen, we've used up all 17 of our electrons. And if you count up the number of electrons around nitrogen after that, you end up with 2 single bonds, and a single electron gives you 5 electrons. We're not going to be able to complete the octet for nitrogen, but we can do better than 5. So you can take a lone pair from one of the oxygens and turn it into a second bonding pair between your nitrogen and oxygens, and you end up with the structure that you see here, where we have a nitrogen-oxygen double bond. That oxygen has 2 lone pairs around it, a nitrogen-oxygen single bond, and that oxygen will have 3 lone pairs on it, and just 1 electron around our nitrogen atom. So this is a free radical since we have an unpaired electron around our nitrogen.